Hello, welcome to my lecture about modern GPU architectures. My name is Nicholas. Please sit back and relax. In this lecture, I'm going to talk about the CPU, GPU, DSP, and FPGA architectures, and I will also be doing a performance evaluation. Also, I will talk about heterogeneous architectures, the evolution of GPUs, the unified scalar shader architecture, stream processing, a comparison of recent GPU streaming processor architectures, and also briefly we'll talk about CUDA. Let's get into it. First, I will explain the difference between what a CPU, GPU, DSP, and FPGA architectures are. After that, I will do a little performance evaluation to compare them. The CPU essentially has wires which go on and off to control what is happening. There is a particular wire in every CPU to keep everything synchronized. This is called the clock. In modern CPUs, we measure it by gigahertz, G meaning billion and hertz meaning times per second. This allows CPUs to do very complicated things very quickly. For example, a 4 gigahertz processor will do 4 billion, will clock 4 billion times per second. The memory holds both data and instructions. The arithmetic and logic gate unit is capable of performing arithmetic and logic operations on data. A processor register is a quickly accessible location available to a digital processor central processing unit. Registers usually consist of small amount of fast storage, although some registers have specific hardware functions and may be read-only or write-only. The control unit controls the flow of data within the CPU. Output arrives into CPU via bus, and output exits the CPU via bus. The CPU has two main parts. The first is the ALU, the arithmetic logic unit, which executes all calculations within the CPU. Also, there is the control unit, or referred to as CU, which coordinates how data moves around in the CPU. The CPU also has three buses. The first is the address bus, which carries the address of the instruction or data. Second is the data bus, which carries data between the processor and the memory. And the third one is the control bus. This sends control signals such as memory read or memory write. Together, these buses may be referred to as system bus or the front side bus. Registers are memory location within the actual processor that work at very fast speeds. It stores instructions which await to be decoded or executed. So the PC register or program counter stores the address of the next instruction in the RAM. The MAR or memory address register stores the address of the current instruction being executed. The MDR, the memory data register, stores the data that is to be sent to or fetched from memory. The CIR, the current instruction register, stores actual instruction that is being decoded and executed. And the ACC, or the accumulator, stores the result of these calculations. So this is how the CPU works, very briefly. Next, we move on to the GPU. A GPU consists of 4 to 8 CPU cores, while the GPU consists of hundreds of smaller cores. Together they operate to crunch through the data in the application. This massively parallel architecture is what gives the GPU its high compute performance There are a number of GPU accelerated applications that provide an easy way to access high-performance computing. Compared to a CPU, a GPU works with fewer and relatively small memory cache layers. Reason being is that the GPU has more transistors dedicated to computation, meaning it cares less how long it takes to retrieve data from the memory. A single GPU device consists of multiple processor clusters that contain multiple streaming multiprocessors. Each streaming multiprocessor accommodates a layer 1 instruction cache with its associated cores. Typically, one streaming multiprocessor uses a dedicated layer 1 cache and a shared layer 2 cache before pulling data from the global GDDR5 memory. Its architecture is tolerant of memory latency. Next, we move on to the DSP, or known as the Digital Signal Processor. It is a specialized microprocessor, or sometimes referred to as a SIP block. It is a chip with its architecture optimized for the operational needs of digital processing. DSPs are fabricated on MOS integrated circuit chips. The goal of a DSP is usually to measure, filter, or compress continuous real-world analog signals, for example, temperature. This is a typical DSP architecture. Digital signal processors are designed to implement tasks in parallel. The DSP contains these key components. So first is the program memory, which stores the programs the DSP will use to process data. The data memory, which stores the information to be processed. The compute engine, which performs the math processing, accessing the program from the program memory and the data from the data memory. Input and output serves a range of functions connected to the outside world. Digital signal processors take our real-world signals like voice, audio, video, temperature, pressure, or position that have been digitalized and then mathematically manipulate them. A DSP is designed for performing mathematical functions like add, subtract, and divide very quickly. The SHARC is a Harvard Architecture World addressed VLIW processor. It knows nothing of 8-bit or 16-bit values, since each address is used to point to a whole 32-bit word, not just an octet. It is thus neither little endian nor big endian, though a compiler may use either convention if it implements a 64-bit data and or some way to pack multiple 8-bit or 16-bit values into a 32-bit world. Analog devices choose to avoid the issue by using a 32-bit character in their C compiler. The term FPGA stands for Field Programmable Gate Array, and it is a one-type semiconductor logic chip which can be programmed to become almost any kind of system or digital circuit, similar to PLDs. PLDs are limited to hundreds of gates, but FPGAs support thousands of gates. The configuration of the FPGA architecture is generally specified using a language, for example HDL, hardware description language, which is similar to the ones used for ASIC, the application-specific integrated circuit. The general FPGA architecture consists of three types of modules. They are I/O blocks, switch matrix, and wires and configurable logic blocks. The basic FPGA architecture has two-dimensional arrays of logic blocks, which mean for a user to arrange the interconnection between the logic blocks. The logic block contains the MUX, a multiplexer, a D flip-flop, and a LUT. The LUT implements the combinational logical functions. The MUX is used for selection logic, and the flip-flop stores the output of the LUT. The basic building block of the FPGA is the lookup table-based function generator. The number of inputs, the LUT, vary from 3, 4, 6, and even 8 after experiments. Now we have adaptive LUTs that provide two outputs per single LUT with the implementation of two function generators. Xilinx Virtex 5 is the most popular FPGA. It contains a lookup table, LUT, which is connected with MUX and flip-flop as mentioned earlier. Present FPGA consists of about hundreds of thousands of configurable logic blocks. For configuring the FPGA, ModelSim and Xilinx ISE softwares are used to generate a bitstream file and for development. As mentioned earlier, there is a little performance evaluation between CPU, FPGA, GPU, and DSPs. The traditional sequential processor is for general purpose applications. The FPGA is a flexible collection of logic elements and IP blocks that can be configured and changed in the field. The GPU was originally designed for graphics, but now it's used in a variety of computationally intensive applications, and the DSPs are custom integrated circuits optimized for an end application. Processing-wise, the CPU is a single and multi-core MCU and MPU plus specialized blocks. The FPGA is configured for an application. SoCs include hard or soft IP cores, and the GPU includes thousands of identical processor cores. And the DSPs, as mentioned, they are application specific and they may include third-party IP cores. There is more of a performance evaluation, which will be explained a bit more deeply and thoroughly in the report, but for now I have just done a small table. It's worth mentioning some weaknesses. The CPU OS operation system capability adds high overhead, optimized for sequential processing with limited parallelism. The FPGA is relatively difficult to program and has the second longest development time. Poor performance for sequential operations, and it's not good for floating point operations. The GPU has high power consumption, not suited to some algorithms, and problems must be reformulated to take advantage of parallelism, but API frameworks provide abstraction. And DSPs have the longest development time, high cost, and cannot be rechanged without redesigning the silicon. It's also worth considering how these choices stack up in some common applications. As shown in the table, designers can often use any or all of the options, either alone or more likely in combination. As the table sort of clearly explains it, the CPU is not really usable or not really recommended for vision and image processing, and we can see that, for example, the GPU is probably the best suit for AI training. This will all be explained in the report a bit thoroughly. Next, let's move on to heterogeneous architectures. Heterogeneous system architectures, or HSA, is a cross-vendor set of specifications that allow for the integration of the central processing units and graphics processors on the same bus with shared memory and tasks. CUDA and OpenCL, as well as most other fairly advanced programming languages, can use HSA to increase their execution performance. Heterogeneous computing is widely used in a system-on-chip devices such as tablets, smartphones, and other mobile devices, and video game consoles. HSA allows programs to use graphics processors for floating point calculations without separate memory scheduling. HSA creates an improved processor design that exposes the benefits and capabilities of mainstream programmable compute elements working together seamlessly. With HSA, applications can create data structures in a single unified address space and can initiate work items on the hardware most appropriate for a given task. Sharing data between compute elements is as simple as sending a pointer. Multiple compute tasks can work on the same coherent memory regions, utilizing barriers and atomic memory operations as needed to maintain data synchronization. Heterogeneous computing itself refers to systems that contain multiple processing units, combined CPU and the GPU, or DSPs, or any type of application-specific integrated circuit. The system architecture allows any accelerator, for instance a graphics processor, to operate at the same level as the system CPU. Among its main features, HSA defines a unified virtual address space for compute devices, where GPUs traditionally have their own memory, separate from the main CPU memory. HSA requires these devices to share page tables so that device can exchange data by sharing pointers. This is to be supported by custom memory management units. To render interoperability possible and also to ease various aspects of programming, HSA intended to be ISA agnostic for both CPUs and accelerators and to support high-level languages. The HSA specifications cover three layers, three parts. The HSA intermediate layer is a virtual instruction set for parallel programs, similar to LLVM, intermediate representation of SPIR. It's finalized to a specific instruction set by a JIT compiler. Make late decisions on which core should run a task, and they are explicitly parallel. The HSA memory module is compatible with C++, OpenCL, Java, and .NET memory modules. It's relaxed consistency and is designed to support both managed languages and unmanaged languages. And the HSA dispatcher and runtime is designed to enable heterogeneous tasks queuing, a work queue per core, distribution of work into queues, load balancing by work stealing. Any core can schedule for work for any other, including itself. It brings significant reductions of overhead of scheduling work for core. Mobile devices are one of the HSA applications area in which it yields improved power efficiency. Another example of a heterogeneous architecture is a GPGPU, explained a little bit later in the lecture. Briefly, let's talk about how GPU started and how they evolved over time. Between the period of 1976 and 1995, the first true 3D graphics started with early display controllers known as video shifters. They acted as pass-through between main processors and the display. In 1978, Motorola unveiled the MC6845 video address generator. This became the basis for the IBM PC's monochrome and color display adapter cards, which were used in 1981. This is a picture of one of these cards. A similar solution from the Commodore's MOS Tech subsidiary, the VIC, provided graphics outputs for the 1980 to 1983 vintage Commodore home computers. The next steps in the graphics evolution were primarily in the professional fields. The advent of color monitors and the lack of standard among the array of competitors ultimately led to the formation of the Video Electronic Standards Association, or VESA, of which ATI was founding member, along with NEC and 6 other graphics adapter manufacturers. The EGA Wonder series The EGA Wonder series 1 to 4 arrived in featuring 256 kilobytes of DRAM, as well as compatibility with CGA, EGA, MDA emulation with up to 640 times 350 resolution and 16 colors. ATI was far from being alone riding the wave of consumer appetite for personal computing. S3 Graphics was formed in early 1989 and produced its first 2D accelerator chip and graphics card 18 months later. The S3 911, which was funnily named after Porsche 911, key specs for the latter included 1 megabyte of VRAM and the 16-bit color support. In January 1992, Silicon Graphics, or SGI, released OpenGL 1.0, which is a multi-platform render agnostic application programming interface, both for 2D and 3D graphics. OpenGL evolved from SGI's proprietary API called Iris. Initially, OpenGL was aimed at the professional Unix-based markets, but the developer-friendly support for extension implementation was quickly adopted for 3D gaming. By 1993, the market volatility had been already forced a number of graphics companies to withdraw from the business or to be absorbed by competitors. NVIDIA launched their first graphics chip, the NV1, in May 1995, and it became the first commercial graphics processor capable to do 3D rendering, video acceleration, and integrated GUI acceleration. Between 1995 and 1999, it was mainly about 3dfx's Voodoo graphics cards. The Voodoo graphics revolutionized computer graphics nearly overnight and rendered many other designs obsolete, including a vast swathe of 2D-only graphics producers. Quantum 3D was spun off from 3dfx on March 1997. SGI and Gemini Technology partnered with the company to work on a very high-end enthusiast and professional graphics solution, leveling on 3dfx's new SLI. It also increased the maximum screen resolution from 800 by 600 pixels to 1024 times 768 pixels. In the summer of '97, 3dfx announced its initial public offering and launched the Voodoo Rush in an attempt to offer a single card with the 2D and 3D capability, but it didn't quite work out. Graphics card back then, they had a separate 2D and a separate 3D card which were connected, and then that was connected to the monitor. 3dfx cut the right corners of pipeline, reducing gate count without much impact on image quality. The Voodoo was easy to program and hard to slow down. The only thing 3dfx was missing was a complete 2D and 3D solution. The NVIDIA GeForce 256 was the first graphics chip to actually be called a GPU, based on the addition of a hardware-based transformation and lightning engine, or referred to as T&L. Building on the strides in between the 2000 and 2006, it was when the NVIDIA versus ATI era began. These two companies started really competing with each other. Building on the strides made with the GeForce 2 series, NVIDIA unveiled the GeForce 3 in 2001, and it was priced around $400. The card became the new king of the hill, but it really only came into its own at then extreme resolution of 1600 by 1200, preferably with full screen anti-aliasing applied. There was also LMA, Lightspeed Memory Architecture support, basically NVIDIA's version of Hyper-Z. It was for cooling pixels that would end up hidden behind others on screen. NVIDIA's product line later added the NV2A, a derivative of the GeForce 3 with GeForce 4 attributes that was actually used in the Microsoft Xbox game console. As NVIDIA implemented the GF3 lineup with underdock TI-200 and overclock TI-500 models, ATI hurried to ramp up deliveries of their Radeon 8 500. The card was built around the R2000 GPU using TSMC's 15nm processes, which were the same used by the GeForce 3. In the higher volume mainstream market, the 760 GT and the GS both provided a solid performance and remarkable longevity, while ATI's X1950 and Crossfire ruled the top-end enthusiast benchmarks for single GPU cards. The X1900 and the GeForce 7900 were fairly evenly matched in the upper mainstream bracket. After 21 years as an independent company, ATI was bought out by AMD in 2006. 2 weeks after the ATI buyout, NVIDIA ushered in the age of unified shader architectures for PC graphics. Aided by the new coverage sample anti-aliasing, NVIDIA had the satisfaction of seeing the GTX demolish every single dual graphics competitor in outright performance. The 48700s and the 4850s become the first consumer graphics to use GGDR memory. Over the years, NVIDIA continued to diversify their feature set in GPUs by introducing Kepler architecture, NVIDIA realized that more cores running at slower speeds are more efficient for parallel workloads than fewer cores running at twice the frequency. Reducing the shader clock also has the advantage of lowering the power consumption, and NVIDIA further economized on the design by drastically reducing the dies available double precision units, as well as reducing the bus width to a more mainstream 256-bit. A general purpose GPU, GPU is a graphics processing unit that performs non-specialized calculations that would typically be used by the CPU. Ordinarily, as we know, the GPU is dedicated for graphics rendering, but the GPUs are used for tasks that were formerly the domain of high-power CPUs, such as physics calculations, encryption and decryption, and also scientific computation and the generation of cryptocurrencies such as Bitcoin. Because graphics cards are constructed for massive parallelism, they can dwarf the calculation rate of even the most powerful CPUs for many parallel processing tasks. The same shader cores that allow multiple pixels to be rendered simultaneously can similarly process streams of data at the same time. That's it for the evolution of GPUs. Now we move on to the unified scalar shader architecture. The unified shading architecture is a hardware design by which all shader processing units of a piece of graphics hardware are capable of handling any type of shading tasks. Most often, unified shading architecture hardware is composed of an array of computing units and some form of dynamic scheduling balancing system that ensures that all of the computational units are kept working as often as possible. The unified shader model uses the same hardware resources for both vertex and fragment processing. The unified shader architecture allows more flexible use of the graphics rendering hardware. For example, in a situation with a heavy geometry workload, the system could allocate most computing units to run vertex and geometry shaders. In cases with less vertex workload and a heavy pixel load, more computing units could be allocated to run pixel shaders. While unified shading architecture hardware and unified shader modeling programming interfaces are not a requirement for each other, a unified architecture is most sensible when designing hardware intended to support API offering a unified shader model. Earlier GPUs generally included two types of shader hardware, with the vertex shaders having considerably more instructions than the simpler pixel shaders. This lowered the cost of implementation of the GPU as a whole and allowed more shaders in a total on single unit. This was at the cost of making the system less flexible and sometimes leaving one of the set shaders idle if the workload used one more than the other. As improvements in fabrication continued, this distinction became less useful. ATI Technologies introduced unified architecture on the hardware they developed for the Xbox 360. And now, just going to briefly explain what stream processing it is. Firstly, we need to understand that CPUs are low latency, low throughput processors, and GPUs are high latency and high throughput processors. Stream processing is a computer programming paradigm that allows some applications to more easily exploit a limited form of parallel processing. Such applications can use multiple computational units, such as the floating point unit on a graphics processing unit or field programmable gate arrays or FPGAs, without explicitly managing allocation, synchronization, or communications among these units. The stream processing paradigm simplifies the parallel software and hardware by restricting the parallel computation that can be performed. Given a sequence of data, a series of operations is applied to each element in the stream. Kernel functions are usually pipelined, and optimal local on-chip memory reuse is attempted in order to minimize the loss of bandwidth accredited to external memory interaction. As clearly shown in the graph, bandwidth of GPUs over the years has skyrocketed, whereas CPUs sort of stayed at the same level throughout the 2000s. GPUs use various optimizations to improve throughput, some on-chip memory and local caches to reduce bandwidth to external memory, batch groups of threads to minimize incoherent memory access. Bad access patterns will lead to high latency and thread stalls. To eliminate unnecessary operations by exiting or killing threads, for example, Z calling and early Z to kill pixels, which will not be displayed. The GPUs use stream processing to achieve a high throughput. A GPU is designed to solve problems that tolerate high latencies. So a high latency tolerance is sort of equivalent of a lower cache requirement. Less transistor area for cache results in more area for computing units, and more computing units is also 10,000s of SMID threads and high throughput. GPUs are good at stream processing. Next, I'm going to compare two recent streaming processor architectures. I'm going to compare NVIDIA's Pascal with AMD's RDNA. In March 2014, NVIDIA announced that the successor to Maxwell would be the Pascal microarchitecture. It was released in 2017, and the Tesla P100 has different versions of Pascal architecture compared to the GTX GPUs. The Tesla uses the GP100 chip, and the GTX GPUs use the GP104 chip. The shader units in the GP104 chips have a Maxwell-like design. The architectural improvements of the GP104 include the following. Its CUDA compute capability with 6.1, GDDR5X, which is a new memory standard supporting 10 GB per second data rates, and updated memory controller. It also has simultaneous multi-projection, resulting in generating multiple projections of a single geometry stream as it enters the SMP engine from the upstream shader stages. Also had DisplayPort 1.4 and HDMI 2.0, and 4th generation data color compression. Also had an enhanced SLI interface with higher bandwidth compared to previous versions. It also had a GPU boost 3.0. The next, AMD's RDNA, is the first product lineup featuring the RDNA. It's the RX 5000 series of video cards, launched in 2009. The architecture features new processor design, although the first details released at AMD's Computex keynote hints at the aspects from the previous graphics core architecture be still used. It features GDDR6 memory and a completely revised architecture. Starting with the architecture itself, one of the biggest changes for the RDNA is the width of a wavefront, the fundamental group of work. GCN in all of its iterations was 64 threads wide, meaning 64 threads were bundled together into a single wavefront for execution. The RDNA drops this to a native 32 threads wide. At the same time, AMD expanded the width of their SMIDs from 16 to 32 slots, meaning the size of the wavefront now matches the SMID size. The RDNA also introduces working primitive shaders. While the feature was present in the hardware of the Vega architecture, it was difficult to get real-world performance boost from, and thus AMD never enabled it. The display controller in RDNA has been updated to support display stream compression, allowing output in 4K or HDR. Comparing the two architectures, the 5700 XT and the 1080 have a similar architecture spec, which provides a good opportunity to compare RDNA with Pascal. AMD claims that the performance of the 5700 XT is roughly equal to a 2070, which is around 10% higher of a 1080 graphics card. However, the 5700 uses plus 45 watt of power. Overclocking 1080 with extra power will mostly close this performance gap. So from rough architectural standpoint, the RDNA has the similar performance, perhaps even a small advantage compared to NVIDIA's 3-year-old Pascal. But to reach this performance, AMD needed 43% more transistors and 40% more memory bandwidth, and most importantly, 7nm process node with its power and clock speed advantages. Now going to talk about streaming processing for graphics. Most newer video cards have stream processors built into their graphics processing unit. The GPU may also be built into the motherboard or the central processing unit itself. The stream processors in the GPU handle most of the traditional graphics rendering tasks, or can be alternatively programmed for more general purpose number crunching. Stream processors are well suited for traditional GPU-focused tasks such as image, video, and signal processing. It's becoming increasingly common to utilize the stream processors on the GPU for both general purpose and scientific number crunching. Stream processing techniques work well for ray tracing or computational fluid dynamics and weather modeling. Applications require massive vector operations and high throughput computations. The number of stream processors are not the only significant measurement for GPU performance. Different GPUs have varying clock speeds between the GPU itself, the memory, and the processors. They also have a different architecture and bandwidth constraints between these separate components. All of this together determines the effective performance of the GPU as a whole. Applications wanting to use stream processing must be designed from the start to effectively sort of take advantage of this technology. Not all programs will benefit, and most general purpose business applications will see limited to no speed up versus the huge gains realized from a very specialized program. Steam processing is suitable for programs that require high computational intensity that fit parallel execution models. The last point to talk about very briefly is CUDA. CUDA, or Compute Unified Device Architecture, is a parallel computing platform and application programming interface created by NVIDIA. It allows software developers and software engineers to use CUDA-enabled graphics processing units for general purpose processing. An approach termed GPGPU, the CUDA platform, is a software layer that gives direct access to the GPU's virtual instruction set and parallel computational elements for the execution of compute kernels. The CUDA platform is designed to work with programming languages such as C, C++, and Fortran. This accessibility makes it easier for specialists in parallel programming to use GPU resources, in contrast to prior APIs like Direct3 and OpenGL, which required advanced skills in graphic programming. CUDA-powered GPUs also support programming frameworks such as OpenACC and OpenCL and HIP by compiling such code to CUDA. When CUDA was first introduced by NVIDIA, the name was an acronym for Compute Unified Device Architecture, but NVIDIA subsequently dropped the common use of the acronym. That's it for this, almost exactly 45 minutes. Thanks for watching my video, and take care.